बिस्मिल्लाहिर्रहमानिर्रहीम। डियर स्टूडेंट्स, अस्सलामु अलैकुम। आज का लेक्चर इस दुआ के साथ हम शुरू करते हैं कि खुदावंद मुताल तमाम आलम इंसानियत को अपने हिफ्ज़ व ईमान में जगह अनायत फरमाए और सबकी हिफाजत फरमाए। Dear students, as you know, we are studying about the radionuclide decay processes. In this regard, today our second part of this lecture. In previous lecture, we have studied about how many nuclides up till now have been discovered, how many nuclides are stable and unstable, what type of parameters are there, factors are there which actually govern in the nucleus in order to destabilize the nuclide, and what kind of processes are there which are responsible to stabilize the nucleus. So there are about 6 processes that actually play a role in order to stabilize the nucleus. For example, spontaneous fission, alpha particle decay process, beta particle decay process, positron ray emission process, electron capturing process, and isomeric transition processes. So these are the 6 processes which play a role in order to stabilize the nucleus. Actually, why these processes carried out occur inside the nucleus? In order to arrange the neutron and proton inside the nucleus for stable configuration, for stable arrangement, and in order to maintain the N over Z ratio, which is responsible for a particular type of nuclide for its stability. Yes, we also studied about the nuclide graph, which represent all the nuclide up till now have been discovered, and the fate of all these nuclide also mentioned over this graph in order to mention what type of decay process they may adopt to become stabilized. In this graph, as in our previous lecture, we studied the black dots actually showing the stable nuclide of an element, and rest of the dots, the rest of the colored boxes are unstable and always trying to be stabilized and get the black position. So if we just keenly look over this graph, the graph in horizontal line, the dots and the boxes at horizontal line showing the similar atomic number, and the boxes in the vertical line showing the similar neutron number. So it's mean all the nuclides which actually occupied the horizontal line having same proton number but different neutron number. So it's mean all these are the isotopes of an element. And similarly, the element which actually the nuclide actually on the vertical line, similar vertical line, all have same neutron number but different proton number. So such type of nuclides are known as isotones. So in this regard, there are two kinds of mainly elements nuclides are there over this graph. One is above the stable diagonal line and other below the stable diagonal line. Which are above the stable diagonal lines, they actually showing the highest number of proton and less number of neutron, and on the lower position of this diagonal line there are which are showing with light sky color, this shows more neutron number but less proton number. So due to this reason, it is well explained that if there is um, more or than a nuclide rich in proton number, it will always trying to reduce its proton number by disintegrating the protons. And other is if it has rich in neutron number, then it definitely disintegrate the neutron to reduce its neutron number to get the stable position. This is one way. Another way is that if we see about this fact, have a look on this line, this line. It shows one nucleide. It shows one nucleide. Okay. This is one nucleide. This is one nucleide. But what you can think that this is not one nucleide. 1, 2, 3, 4, 5, 6, 7, 8, 9. So all these 8 boxes on this line have the same proton number but different neutron number. It means there are about 9 nucleides which are stable for one proton number. So it's mean as we have studied in previous lecture, there are 272 nucleides which are stable. It's mean we have only 118 element which are placed in the periodic table. So there are at least one configuration of neutron and proton number is that which showing the stable configuration for a nuclide for an element. But this is not restricted to one, but there are so many elements are those which showing more than one nucleides which are stable in nature. So if we see the atomic number, lower atomic number elements have few or one or only two such nuclei which are stable. But if we go at the middle of the periodic table where this atomic number is 15, at that point or around that point there are more than 1, 2, 3, 4, 5 such nucleides which are stable in nature. So rest of the nucleides which are representing with the different other than black color are unstable and have different kinds of decay processes that we are studying. Okay, so if there is n over z ratio less than stability value, it will be in rich in proton number that will disintegrate into neutron. But if it is less n over z value is greater than stability value, then it will be enriched in neutron number and will be disintegrated into proton. Okay, so let's see the first about the new spontaneous fission. So spontaneous fission, that is a process that occur commonly inside the nucleides of heavy elements like that more than if atomic number is more than 82. So spontaneous fission can proceed in that nucleides. In this process, a nucleus may spontaneously or sometime by the bombardment of a neutron, they fissile into two components having ratio of a proton number 60 and 40. And in this regard, along with this fragmentation of one heavy nucleus into two data nucleides having a ratio of proton number 60 and 40, they also emit a huge amount of energy, like that about 200 mega electron volt energy. Other thing, the probability of spontaneous fission is low and increase with mass number of the heavy nuclei. So most of the time, we do this fission by the bombardment of neutrons. If we see about the spontaneous fission without bombardment of the proton over the target material, which having the highest heavy nucleus more than atomic number more than 82. So there is an example of a uranium 235. This uranium 235 have half-life 2 into 10 raised per 17 years. So in 2 into 10 raised per 17 years, in 2 into 10 raised per 17 years, the concentration of uranium 235 itself reduced to half without any bombardment of neutron over this material. So it disintegrated it fissile into two 60-40 ratio components. And other thing is that if we see another atom nuclide or element which having the 55 days half-life, that is CF254. So it has a more nuclei inside the nucleus. There are 254 nuclei in its nucleus, but if we see about uranium, that has only 235 nuclei in its nucleus. So due to this reason, it is much heavier as compared to uranium, and therefore it cannot bind its nuclei too much tightly. So due to this reason, this nucleus spontaneously fissile in shorter period. So no need for the bombardment of a neutron over the this material, but it within a 55 days its concentration reduced to half due to the heavy nucleus, more and more heavy nucleus. So this is the spontaneous fission. If we take the example of like so uranium when spontaneously fissile into its daughter component, that barium and krypton is formed with 60 to 40 ratio with the emission of two neutron. However, if we bombard an neutron from outer source over this target material, then this would be 3 neutron or 4 neutron. Okay. Another example of this is that FM2656. So this nuclide, if we see, it also have heavy, much more nuclei in its nucleus. Due to this reason, it also undergo spontaneous fission with the emission of 4 neutron. Another thing, what actually happened in this process over our result, what actually we obtain after the emission of this. Before emission, energy is at highest point because it is in an excited state, because so many nuclei inside the nucleus, and it is very difficult for a nucleus to hold all these component or nuclei in its stable configuration, because there is a strong repulsive forces also hold inside the nucleus. Due to this reason, it trying to hold all the nuclei inside the nucleus, but in order to destabilization due to heavy nucleus, it undergo spontaneous fission. If undergo spontaneous fission, it emits energy and the system appear as a in ground state. So energy of the system going to reduce, and in this way the atomic nucleus become stabilized by the fragmentation process. Okay. The other part is alpha decay. The second most important uh, decay process is alpha decay. What is meant by alpha decay? Usually heavy nuclei such as radon, uranium, neptunium, and so forth decay by alpha particle emission. The alpha particle is a helium ion containing two proton and two neutron, but no electron. This is helium nuclei, not helium atom. So alpha particle is helium nuclei, mean there is a nucleon number inside the alpha particle nucleus, just like that of a helium atom, but together in the nucleus. In alpha decay, the atomic number of the parent nuclide is therefore reduced by 2. Yes. So because alpha particle emitted from a heavy nucleus with the emission of two proton and two neutron. So it's mean if there is a reduction of two proton in the nucleus of the parent element, so there is a reduction of two atomic number. And similarly, if we see there is a two proton and two neutron reduced in the parent nuclei, so there are atomic mass reduced by 4 nucleons and the mass number by 4. An example of alpha decay is uh, 235 92 uranium and undergo alpha decay process. So due to this reason, helium is formed with 90 atomic number and 231 atomic mass. So here is a reduction in 4 number in atomic mass and 2 in atomic number by the emission of helium nuclei. An alpha transition may be followed by a beta emission or gamma ray emission or both. So it is more important point here to understand that it is you should not be considered that if there is a alpha particle emitted from the nucleus of an heavy element and the daughter nuclei will be highly stable. No, it is not at all the situation, but they undergo in order to rearrangement their new nucleus. So in order to rearrange, in order to get the configuration of a stable nucleus, so they have to emit further beta radiation emission or gamma radiation emission, or sometimes both radiation also emitted. First beta radiation emission occur and then accompanied with this process there is gamma radiation emission. But if there is no beta radiation emission, then only gamma radiation emission take place. The alpha particles are monoenergetic and their range in matter is very short, on the order of 10 raised by minus 6 centimeter, and is approximately 0.03 millimeter in body tissues. So in nuclide graph you study that there is the the atomic number with more than 62, okay, sorry, 82 atomic number, more than 82. All these elements most probably undergo alpha particle emission. So those elements which actually have atomic number more than 82, they undergo most probably by alpha particle decay process through alpha particle in order to stabilize. Okay, this is equation of alpha decay. This is a parent element in atomic mass reduction in 4 number and atomic number reduction in 2 number, and helium nuclei is also proceeded along with this process. So this is another visualization of the alpha decay process. If we see uranium decay into alpha particle and also give the thallium, and this thallium stabilize itself by the nucleus de-excited by the emission of a gamma radiation emission, and thallium is produced. So this is a excited state of thallium and this is the ground state of thallium. So this is another example of alpha decay in which plutonium is decayed into uranium with the emission of helium nucleus. Okay. So next decay is okay. This is another alpha decay is very important with respect to uh, application point of view, particularly today. You know, my dear students, there are so many strategies in order to deal the cancer, but most of the strategies are looking not so successful. So having some issues, having some efficiency problems. Due to this reason, nuclear medicine proceeded in this regard very efficiently, and particularly with respect to alpha decay process. As you know, alpha decay is that alpha particle are those particles which have only 0.03 millimeter in body tissues. So most of the in recent days, in recent era, the scientists are going to label these atoms which actually decaying through alpha particle. They emit radiation, and these particles are actually so these alpha emitter radionuclides are attached to some kind of biomolecule. These biomolecules have specificity for cancer molecules. So this biomolecule, this is actually antibody. Antibody is attached with some kind of a linker and chelator, and because most of the radionuclide direct cannot be directly labeled with antibodies or biomolecules. So in order to label these alpha particles, radionuclides with some kind of biomolecule which have specific target inside the body for cancer and have specificity for cancer molecule or infection molecule. They are modified through linker and chelator, and then this chelator have making a complex with alpha particles, alpha nucleides, and when these are injected inside the body, they go into the body and attach through receptors with the cancer cells. So these receptors through endocytosis process engulfed by the cancer cell, and whole of this molecule go inside the cancer. And this radionuclide having uh, penetration power in nucleus in tissues only 0.03 millimeter. So due to this reason, and this is highly localized, and inside when they go inside the cancer cell, due to very heavy ionization power as well as burning power, they destroy the whole cancer cell. So in this regard, today very successfully prostate cancer is treated with the help of actinium labeled antibodies, which actually go at the prostate cancer and destroy and burn the cancer cells very rapidly and very quickly. So this is the main application of alpha therapy in nuclear medicines. So there are so many other examples of in which alpha radionuclides are labeled with the biomolecules, and that molecules are injected when into the patient, and they all accumulate at specifically at the cancer cells. That due to that reason, all the cancer cells burn very quickly. Although this therapy is very costly, but after adopting this therapy, it is more confident a patient that it will be recovered very quickly. So this is the disintegration equation of actinium, which is the best used in the nuclear medicine field. Actinium having very excellent half-life 10 days, and it undergo francium 221 alpha particle emitter. This element or nuclide have only 4.8 minute or you say that half-life. After 4.8 minutes, it undergo the alpha emission again and give 80 to 17, and other is bismuth to 13 after 0.032 second. So this is the main element nucleide which undergo the alpha decay process after in 10 days with 10 days half-life. So it can be used for a long time if we purchase a nucleide from any source. So it could be uh, used for number of days, because after 10 days its concentration reduced to half, and further other 10 days further it reduced to half. So due to this long half-life, it could be easily used at different medical centers and could be import from foreign countries with full confidence the concentration or activity of the actinium remain safe. Okay, so this is an other decay process which accompanied with the emission of a beta radiation. So if we see about the beta decay processes, why actually beta decay process proceed inside the nucleus when a nucleus is neutron rich, that is has a higher neutron to Z ratio. It means there is a neutron number enriched inside the nucleus. So when neutron number is rich inside the nucleus, so in order to reduce its number, neutron will be disintegrated. Compared to the stable nucleus, it decays by beta particle emission along with an antineutrino. An antineutrino is an entity almost without mass and charge, and is primarily needed to conserve energy in the decay process. So it is responsible for the energy, which is a difference of energy between a parent and a daughter nucleide. So it accompanied with the energy which is actually the difference of parent and daughter nuclei. In beta decay, a neutron essentially decays into a proton and a beta particle. For example, a neutron when disintegrated, a neutron it disintegrates into a proton and beta particle plus antineutrino. The beta particle is emitted with variable energy from 0 up to the decay energy. Yes. The decay or transition energy is the difference in energy between the parent and daughter nucleide. So this would be the transition energy, decay or transition energy, that is actually the difference between this energy and this energy. So most of the energy will be carried out by this beta particle, but rest of the energy that is still less as compared to the parent nucleide, that will hold by this neutrino antineutrino, that is also known as decay or transition energy. Okay, as antineutrino carries away the difference between the beta particle energy and the decay energy, the beta decay may be followed by gamma ray emission. Okay, as we studied in a previous slide, if there is a beta ray emission carried out, it is necessarily there should be gamma ray emission. In order, because one thing you should be know, at if neutron is there is, according to quantum mechanics and quantum theory, there is a certain arrangement of proton and certain arrangement of neutron inside the nucleus, and where are neutron present, there is no need of putting the proton have its own shells and inside the nucleus, and neutron has its own path inside the nucleus. So if there is a neutron disintegrated into a proton and beta radiation emission, so actually proton is produced or formed at the place of neutron, so it should have to move or shift the position of neutron to proton. So in order to doing this, when a neutron, when at this place where is a neutron is present and now the proton is have formed there, so proton from this position should have to move from neutron position to proton position. To do this process, in order to shifting process of a proton from neutron position to now and its proton orbitals, so the emission of gamma radiation takes place. If the daughter nucleide is an excited state, and the number of gamma rays emitted depends on the excitation energy. After beta decay, the atomic number of the daughter nucleide is one more than that of the parent nucleide. However, the mass number remains the same for both nucleide. Okay, you should know that there is a beta decay with the light blue sky color. So these are all the elements, all the nucleides below the stable diagonal. All have ability, all have neutron enrich. So they have more neutron but less proton number. In order to reduce the neutron number, they undergo the neutron disintegration process, mean beta radiation emission. So due to this reason, if we see about the decay equation, in this parent element is here, nuclide is here, and when this nuclide undergo neutron disintegration and beta decay process, what actually happen here, there is plus 1 in proton number, because one proton is produced. So mean in parent radionuclide one more proton appeared formed. So one more proton is formed here. But if we see, if there is a disappearance of one neutron, then appearance of one proton, so nucleon number overall will be same and atomic mass will also be the same. So this is a beta radiation and this is antineutrino as an energy compensation process. Okay, this is an example of beta decay process. Radium and 88 with atomic number and atomic mass number is 28 undergo, it should be below and should be over. Okay, undergo process of this, there should be 228, it should be 8. Okay, 1 minute please, this should be 8 8. Okay, this undergo decay process, and there is one more proton appear. Due to one more proton appearance, atomic number going to 89 and it form actinium, so by the beta emission. So this is another carbon atom also sometime undergo beta particle emission when it is activated in the cyclotron. So this process carried out. So beta is also very important in our in medical field, in nuclear medical medicine field. because it also have the same uh, similar type of activity as actinium, because it have ability to burn the cells in when it is labeled such type of molecules or nucleides. So we are labeled with as we have labeled with the uh, such type biomolecules in place of alpha particle radionuclide. We can also label it with the beta particle radionuclide nuclides. But it should be in your mind the ionizing power or destructive power of alpha particle is much greater as compared to beta particle. But the system situation is that the ion penetration power, beta particle has greater penetration power as compared to alpha particle, and due to this reason it have ability to burn a large area of the tumor cells. Due to this reason, most of the people and most of the clinicians are actually practicing beta emitter radionuclide by tagging with biomolecule in order to treat the cancers. So, dear students, there are so many other examples which actually in which beta particle emitted. This is alpha iodine 131 decay through beta particle emission, iron 59 decay through beta particle emission, molybdenum decay through beta particle emission, and cobalt decay through beta particle emission. Okay, the radioactive decay of a nuclide is represented schematically by decay scheme, and examples of the decay scheme of iodine and molybdenum are given in figure 1 and 2 respectively. So, if we see about this process, all these nuclides emit the and beta radiation emission, and the formation of a new element. These are not still stable, they are in excited state, because in place, as I have discussed in previous slide, there is a formation of a proton at the place of neutron. So there should be a rearrangement inside all these nucleides in order to rearrange in order to get the stable position, stable nuclide. They will emit the gamma radiation emission. So dear students, in next lecture we will further study what will be the effect of beta radiation emission in the production of other kinds of radiations, and how beta particle emission play a role in production of Bremsstrahlung radiation, and like that uh, X-rays radiation, and what will be the effect of all these process after the production of Bremsstrahlung radiation and X radiation. So next up to next lecture, I would like to say Allah Hafiz. Thank you very much.